We'll now go to the second presentation. Clayton Signor will give a presentation about cost savings dealing with driven piles in Central Texas. Clayton, take it away.
All right, you can see me now. Hi, my name is Clayton. I'm the president and owner of Texas Pile in Austin, Texas. I'm going to talk to you about a project we did last year where we drove about 2,055 piles in a matter of 8 weeks of operation time. We got to that point by doing, okay, is that working for me? Okay, there we are. So in the presentation, I'm going to tell you about the background of applying driven piles and expansive soils, which is definitely underutilized out there. The overall project description, the design and testing steps, the pre-production test pile results analysis, and how I extrapolated the final test or final pile design. And then we did 4% of the overall piles with the high strain dynamic pile test. I look at those results and then driving criteria from different areas based off those, production analysis, and then the conclusions. So to start with everything, I don't know if you know anything about Texas, but we have some very highly expansive soils, smectite, Mount Morellite. And also we have some very inconsistent weather events. We're semi-arid, so we get 30 to 35 inches of rain in a year, but we can get 10 inches in an hour and up to 38 inches in 48 hours. So it's a lot. We get our floods and we get our droughts. This causes our active zone or seasonal moisture chain area vary anywhere from 8 to 22 foot. Typical rule of thumb is 12 foot. So in the top 12 foot, that's where you get some swelling, which the PVR, potential vertical rise, is typically about 3 inches, but I've seen on geotech reports up to 10 inches and literature up to 12 inches of movement. So in swelling conditions, it rises, and then in drying conditions, you get surface cracks like this. This is 18 inches, and it's about 5 or 6 inches wide. And so basically you can trip on this. And then if you get it wet, then it all becomes this mess. This is problematic because concrete doesn't like to move more than an inch. And you have a lot of people out there that developed land and didn't have the proper deep foundations. So the two design aspects are you have to look at the dry conditions and the wet conditions. The dry conditions typically govern because theoretically, the worst case scenario is the active zone completely shrinks away. So you have no resistance on your shaft in the active zone. So the structural loads, dead and live loads, have to be resisted by the end bearing pressure and the shaft resistance in active zone. In the wet conditions, the active zone pushes up with the swelling forces, but that can be confined with the dead load of the structure and the inactive resistance in the shaft. Typically, this governs in lightly loaded piles when you don't have the confined dead load above. So some remediation for the expansive soils is remove and replace soil, seen anywhere from 3 to 16 feet, typically 6 to 8 foot. Basically make a raft of soil in 6-inch lifts. You can do lime soil treatments. Grading and landscaping is amazing. I tell all my friends with clay soil conditions, make sure you water your lawn, don't have plants too close to your or trees, and make sure you have proper grading so you don't get bird baths. And a lot of tract homes have shallow foundations where they remove, replace, and do post-tension slabs. And then if you have foundations for buildings that need to be around for a while or cost some money, you need to get into deep foundations. Typically, you do drilled shafts, either straight shafts or you have a under ream at the bottom, about 20 foot to 50 foot. And since I've been around, we've been driving piles and expansive soils, which is still super underutilized. And then these deep foundations support a structural slab, either supported by a carton form or a crawl space. So carton form, I don't know if you're familiar with it, but basically is a cardboard box with some wax on it or some water resistance that they definitely get swamped occasionally or regularly. You put those under the grade beams or the slab, and here's what piles look like when we have the concrete poured in with some dowels in it that will be tied into grade beams or pile caps. And here is example of pier and beam. You can do it with direct wood structure on top of the piles, steel structure, or you can do a carton form concrete structure that also supports the steel structure above it. And in these two situations, we were actually in flood zones, so we were able to get above the grade with the crawl space. So it's the most conservative route for the expansive soil, and also we can deal with the flood loads. So another aspect for our soils to look into when we're doing testing is this paper that Frank Roche wrote in 2018 about soil dampening in high plastic soils. Basically, it comes down to is when you're hitting and testing high plastic soils, you're going to get more resistance because the pore pressure gets excited. And then when that pore pressure dissipates, then you get more loading later. It's kind of like if you hit the sand at a beach, you get more resistance initially, then it tapers off. He found a 70% resistance factor, and later on I'll tell you what we got. So the project was in San Marcos, Texas, about 45 minutes south of Austin. It was 8 modular apartment buildings that were pier and beam and 1 clubhouse slab on grade with void boxes, close to 500,000 square feet of air-conditioned space on 19 acres. The max height was 3 stories, and we drove a little over 2,000 piles. And Z Modular is a subsidiary of Zekelman Industries, which is a big steel producer, and they also own Atlas Tube. So there's a big push of using the Atlas Tube, and that's actually how I got into the project, is through Atlas Tube. The original design with static analysis from the geotech report was 12-inch piles, 30 foot deep, and the final design was 8-inch Schedule 40 piles, 25 foot deep. And also the design load was 59 kips, just so 30 tons. Go back. So to get the final design load, we did a pre-production test pile with 2 static loads and 3 dynamic pile tests on. We loaded with 3. We tested with dynamic pile tests on 3 piles, 2 of the static load and 1 of the reaction piles at initial 1 hour, 1 day, and 7 days to see what the soil setup was. And then production, we did 4% of the total pile. So we did 80 initial and restrikes. And when we did construction, we used a CZM EK125HH, which is a dedicated pile rig with an 8,000 pound hydraulic hammer. And we got 40 to 66 piles in a day. And it took about 8 weeks to complete. Here's a stakeholder list, Z Modular, the owner, here's the structural engineer and the geotech supplier. We're the contractor, and GRL did the testing. So Z Modular, they own a proprietary connection piece that can technically stack up to 7 stories high. They use the steel from Zekelman Industry to do prefabricated modular buildings, 12 by 12 square by 20 to 66 foot long. And then they build those offsite, and during the permit process, they can have everything ready. So once they get the foundation in, then it's just a bunch of Lego set, and then they crane everything on the foundation. And again, our rig is a CZM EKA 125HH, and we only use a 2-foot stroke for everything. So the geotech report showed soil of very stiff to hard clays and plasticity index of 35 to 69, which is typical. You know, the PI, that's extreme in most conditions and anywhere in the world, but for us, that's, again, pretty typical. The initial geotechnical recommendations for the piles was based off static analysis. And remember that the design load was 59 kips. So what they recommend was not going to work. So we had to ask for a WEEP analysis. That way we got a 12-inch pile that had allowable capacity of 64 kips. That was something that we could base the design off of and move forward. But that wasn't good enough because I've done a lot of high strain dynamic pile tests in the last 10 years, and I knew that we could get a lot more capacity. So we went ahead and did a pre-production test pile program where we statically tested an 8-inch and a 12-inch pile. And then we did one of the reaction piles with the open end without a plate. And then we had closed ends on the 8-inch and 12-inch. Here's kind of the schedule we did in October. We did initial 1 hour on the first day. The second day we did a restrike, and a week later we did the static load and dynamic pile test. Here's a site where the pre-production test pile site was. Here's drone footage. You can see our cranes over here. And right here, there's a big drainage area that's taken off like 150 acres. And during our testing program, we had to deal with the creek going through the access road over to the site. So we had to crane over our air compressor to use our air hammer. Here's a reaction beam. Here's my construction manager drilling and tapping for the instruments. The layout for the test piles and reaction piles, driving with our 5,000-pound air hammer, and then just confirming that all the reaction piles were in line. So whenever we do any pile driving, I record blow counts and I keep that records as much as possible. That way I can track everything, make sure that if we get into hard conditions, we can see if that's right or if it's just an anomaly. And from this, I can show you that the 8-inch pile drove pretty easily. That's why we got the 30-foot. And then the 12-inch piles, we couldn't necessarily get the 30-foot because the blow counts were just getting so high. We basically got refusal with our 5,000-pound air hammer. And then when we're doing our high strain dynamic pile tests, I matched the blow counts with the case method capacity from the PDA. And I try to get a trend line so I can, in the future, if we have blow count, I can see what a blow count would be with a relative capacity. Here's the testing frame for an 8-inch pile. Here's the loading curve. It's not perfect. The 12-inch actually had a nice 2-inch drop and then came back. It wasn't perfect because one of the reaction piles actually pulled out. So with a failure of right under 340,000 pounds at 30 feet, we knew that 28-foot 12-inch pile resisted half of that, so 170 kips. Here's a breakdown of all the capacities from the test and the design. You can see for the 8-inch, it goes from 36 for ultimate. Here's allowable, so 18 to 40 to 60. So this is where we're, the initial high strain dynamic pile test, we're getting what we needed. And then the static load test, we had 160 to 170 kips of actual loading, which is amazing. And we did restrikes 187 days later. So remember that we only need 59 kips for our design load. So I was like, well, we're driving over 2,000 piles, so every foot really counts. So I was like, let's see what we can do with 25 foot. So shaving 5 foot after 2,000 feet, that's 10,000 feet times 28 pounds a foot. So I put a factor of safety 2 on everything. I know what the ultimate capacity was. I took the end bearing from the dynamic pile test. I removed the top 10 feet for the dry conditions, and I removed the lower 5 feet because that's what we're trying to reduce for the shaft resistance. So we got a total shaft resistance of 170 kips, and then I reduced it by a dampening factor of 80% that we found from the 12-inch static load versus the 12-inch dynamic pile test. And we're just being a little conservative. And then we got to 100. Basically, when you put everything together, we got a ultimate factor capacity of 200 kips. Put a factor safety of 2 on that, and that's well above the 59 kips, and everyone's happy. So going down to the pile design cost comparison, the original static design, which was not feasible, there's a lot of over 3,000 piles. The cost would have been $8.4 million, and that was with the 12-inch piles, 30-foot deep, and only a design load of 40 kips. It would have taken 6 months to do. Using the WEEP analysis, we use the 12-inch piles at 30 foot, and we would have to add another 4 foot for miscellaneous connections, and if we hit some weak areas. So with a design load of 64 kips, the schedule would have been 16 weeks, and the cost would be 5.62. With the final design based off this pre-production static load test, I reduced the price in half to 2.82 million. And we drove the 8-inch schedule 40 piles to 25 foot, and we had a load capacity of 100 kips, and we took 8 weeks to complete. So in the production, we tested 4% of the overall piles, or 80 total piles at initial and restrike. With that information, I followed these steps that I followed earlier for the when I extrapolated the final pile design. And overall, majority of the piles exceeded a factor of safety of 2.0, and except for close to the drainage area, we had a couple piles in 2 buildings and the clubhouse that we had to order 35-foot pieces instead of the 29 to 30-foot pieces. And there are, I think, about 100 total. Here are the results. You can see overall the minimum was over 2, the median was 2.5 or higher, for most of them besides the clubhouse. Clubhouse was weak soil, as I said earlier. And then these are the 2 pads with there's like 2 or 3 weak piles over there. Here's the blow count versus depth. Pretty large range from 5 to 25 blows per foot down to, these are the weak soils, 11 blows per foot of close to 55 blows a foot at the most. Most of them were between 15 and 30 blows a foot at the end of driving. And then with all the dynamic pile tests, I again graphed the case method from the PDA with the blow counts, just to see what the blow counts were for other for other piles. And R squared value of 0.86 is close enough with this kind of data. And then I compare the case method with the signal matching outcome. And for the most part, the case method was more than signal matching for the initial and the restrike. And the restrike has a nice R squared value of 0.95. So we could reduce the case method to the signal match pretty accurately. And I got Brandon Fedeflace of GRL engineers to do a WEEP analysis overall, back calculating or using our test data to get information for future design purposes. So we looked at the shaft resistance and the end bearing for 0 to 30 feet. So during the dynamic pile test, we do 2 things. One is confirm the capacity. 2 is we get a driving criteria. Overall, the driving criteria was 10 to 16 blows a foot, except for the weak soils. We had to go a little bit deeper. The weak soils were next to this drainage area and caught within these blue lines. Here are the 2 pads I was talking about, and in the clubhouse. During production, we were getting up to 66 piles in a day, and we averaged about 40 piles in a day. There are some times of wet events and also getting over 2,000 pieces of pipe here in San Marcos was not necessarily easy. So depending on the rollings, there were some gaps in construction time. Here's the production pictures, February of 2022. Here's the cesium rig, and then here's our link belt crane with the swinging leads and a 5,000-pound air hammer in the background. We only did 1 pad with that hammer, and then we did all other 7, 8 pads with the cesium. Here are the 3 pads on one side. Each one of these have 300 this one's 350, that's 160, and that's 350 right there of piles. Here's the drainage easement I was talking about. outlined an area. Here's where the clubhouse was going to be and the two other weak areas. And here's the rest of the site. There's a couple other buildings on the other side of the drainage area. And here's where we did our pre-production test pile. So during the process, after we drive it, we cut the piles down. And overall, we only had to do full penetration welds for splicing on 6 locations. 1 pile bent, and then 5 of them were at the clubhouse where we just had to get some extra material on them to get them down through the weak soils. And also the weak soils were not picked up on the geotechnical report, so that the dynamic pile test was the only way to understand that there were weak soils. Here's what the concrete pile caps look like. And first they did the forms, poured them, wrecked the forms, then put the utilities in. And then this is a site rendering of what the final apartment complex will look like. So overall, 8 and 12-inch closing pipe piles can support over 320,000 pounds at 30 and 27 foot respectively. Static analysis and pile driving simulation, like weep analysis, results significantly unpredicted capacity of piles. Soil dampening conservatively was 80% from 70% found in Roche's 2018 paper. Performing a test pile program saves 67% from the static analysis and 50% from the pile driving simulation, and over 2 months of pile driving time from the schedule. In the future, it'll be great to look at open-ended piles versus closed-ended piles, because the static load test reaction pile was open-ended and it showed a lot more capacity than the closed-ended piles. And also the production rate of the cesium rig was 5 to 8 piles an hour and up to 66 piles per day. We have 2 more projects with the same client. One is ongoing in Gerald, Texas, and then which is about an hour north of Austin, and then one in East Austin, close to Manor, where we'll have close to 1,900 piles. If you have any questions, please let me know.
Thanks, Clayton.